This is video number 2, lesson 1. We're going to start with the first learning goal. Determine the vertical stretch or compression of y equals x squared. Now in this video I'm just going to show you a demonstration of what's going to happen in the virtual classroom, and the real work would be done there using the assigned worksheets as I showed you in the previous video. Now let's say I have one quadratic equation, quadratic relation if you want to call it, y equals x squared. This is the basic quadratic relation in general. X to the power of 2, that's a parabola, the graph of that. The vertex is at the origin, 0, 0, it's a minimum point, a is 1. Now if we just take a simple table of values, we know that for x equals 0, just plug in 0 here, you get 0 squared, so 0. For example, plug in x equals 2 in the equation. 2 squared is going to be 4, so it's going to be like 2 and 4. If you plug in negative 2 on, it's going to be like negative 2 squared, so 4 again. And we can know that from the symmetry. Remember, the line of symmetry here on the same level, 2 would be 4 and negative 2 would be 4 again. So now we said that the value of a here is 1. It is positive, and knowing that it's positive, I know that the graph would open up and it's gonna have a minimum point. Now what happens if a is 2 now? Just take a look here what happens if I just change a to 2. You see that the graph gets narrower. Just back to 1, the graph is wider. Let's put 5 for a. Again, it's going to open upward, but again, it's getting narrower and narrower. So let's put 10. Again, it gets like narrower. We would imagine that as if the graph is just stretched upward. So it's getting narrower here, or as if it is like stretched upward. This process here, multiplying the x squared or changing the value of a for a number that is greater than 1, is gonna stretch the curve up. If we make it 100, let's see what happens. It gets narrower even more, or as if it's like stretched even more upward. It is like the same example as you are probably holding a bottle of water and then you squeeze on that bottle of water. It's gonna get narrower from the edges, or the cross section would get narrower. However, the water level would rise. So it's like the same example, if you know what I mean here. So again, that's my parent function, y equals x squared. Multiplying the number here, the x squared, multiplying it by any number, let's say 6, will cause the graph to stretch up, stretch vertically. And we will see that with numbers during the lesson, during the virtual lesson. Now, what happens if we multiply this x squared or change the value of a to be a number that is less than 1, but it's greater than 0, still positive? So let's say a number that is 0.5, 0.6, 0.7, something like that. So let's do 0.5. Let's see what happens. It's getting a bit wider. Let's do like 0.05 probably, and it gets even wider and wider. Let's do 0.2 again. So at, let's say 0.1, it gets wider. That's 0.9. It's almost approximately the same as the original one, which is x squared. So if you see here, as the number multiplied by x, the a value here is smaller, gets smaller and smaller, the wider the curve would be. For example, let me zoom in here just a little bit. So let's make this number as, for example, 0.004. You see that this curve gets narrower and narrower. We would say as if this graph was vertically compressed, as if there is a force acting on it from here and here, like from all the sides, just pressing it downward. So we say that this graph is vertically compressed. It's just getting shorter. So what happens, what really happened in a stretch, for example? Let's go back to the stretch example here. Our original graph. So that's our original graph. When x was 2, let's zoom in more. So when x was 1, 1 squared was 1. So the point would be 1 and 1. Let's sub in here 5. What is the corresponding value for 1 now? If you see 1 goes up here, so let's just do a slight comparison. Y equals x squared. That's the parent graph, or that's the original one, where if x is 1, y is 1. Now in the new graph, the stretched graph, it's just as if this graph was just pulled upward, stretched, and this is my new outcome. If you plug in x equal 1 in this red graph, you would get a value of y equals to 5, which is like 1 squared is 1 times 5. So the new point on the new graph, it is 5. Whatever was applied to 1 could simply be applied to 2. So on the normal, the original, the parent one, it was like 2. Technically it was 4. 2, 4, because 2 squared is 4. Now, what would you expect if you plug in x equals 2 here? What would the value of y be? So remember, 2 squared, 4 times 5, that is 20. So I would expect here on this line to rise until 20. So let's go still here, just one more step. That's my point, 2 and 20. In other words, we call it a stretch because technically all the y values are just multiplied by this number. Because let's say this number wasn't here, it is x squared, it's the normal graph. That's the y values. Whatever y value we get after plugging the x, that would be multiplied by 5, and it's gonna get bigger, larger. That's why we call it it's stretched. On the other hand, if it is like multiplied by 0.5, so just getting back here, just zooming out. So that is the parent function, the blue one, and that's the transformed function, 0.5 x squared. So it is a bit wider. So in a similar fashion, I would expect like the values for y are multiplied by 0.5, so they are halved, then they are getting shorter. Technically, the graph is just dropped down. It's just compressed. So just let's zoom a bit here. Zooming in. So again, for the point 1, 1 squared is 1. That's the original graph, the blue one. 1, 1. What do you expect the value of when you sub in 1 in the transformed graph? I would expect it to be like 0.5 because 1 squared is 1 times 0.5 is going to be 0.5. So again, that is the red graph, the transformed. So 1 and 0.5. Whatever happened with 1 would happen with 2. Remember, on the original graph, 2 squared is 4. So 2 and 4, that's the point. 2 and 4. Again, what would you expect would happen at the red graph? Correct, it's going to be halved. So the 4 would be 2. So my new point would be here 2 and 2. And so on. That's why we call them like the y values are compressed. They are just diminished or getting smaller. And this is the concept of compression. And we call it vertical compression or vertical stretch because it's happening like in the vertical direction. Either the graph is pulled up or pulled down. That is basically what we need to know about vertical stretches and compressions. We're going to work those out in the live classroom using the worksheets. I've also handed out or just posted also the summary or the notes for this. So you do not need to worry about taking notes or just pausing the video every just 5 seconds to write whatever I'm saying. All the notes are there, or the key features or key ideas are also posted there. And that would be it for the first learning goal.